my drawing.
All right, guys, so we had to restart it. So
Okay, so again, why do we care? These IQ signals are the basis for all the RF signal processing that happens in SDRs, and everything from like a flex radio or an anon, or even the wildly popular ICOM 7300 is basically an SDR. So, but IQ signals are what are going on inside. So it's nice to understand what that's all about. IQ signals are as a way of representing signals that can contain all of the information and characteristics of an RF signal over a given bandwidth with very little sample rate and memory storage requirements and things like that. And we're going to talk about why that is here in a moment. So it's helpful, I think, always to understand the basics of these RF signals so you can better convey the benefits of it, and also just to understand what goes on under the hood, so to speak, inside your radios these days. Anybody who does any home brewing might have homebrewed a receiver like a soft rock or something like that. That is a quadrature sampling detector. That's also to create IQ data from the incoming RF. So that's all the same type of thing here. So let's break it down here. Let's kind of start from the basics. First, what is an RF signal, right? An RF signal is simply thought of a sinusoid that's a high enough frequency to support electromagnetic propagation. Okay, the basic equation of a sine wave is here, right? And that's just a basic view of a sine wave on an oscilloscope or virtual oscilloscope here. Where you've got the letter A is the amplitude of that sine wave, what peak voltage it reaches. The letter F is the frequency, how often that signal repeats itself. And T is the time, the progression of time for that. Well, we're going to show you in a minute here why we actually just talk about the basics of this. If we kind of slow the scope way down and look at the RF envelope, we've got a high frequency sinusoid kind of running up and down inside this picture here now. But now if that parameter of A on that sine wave is varied over time, you essentially can amplitude modulate the RF signal. It just looks like an AM RF envelope. Okay, so here A is a function of time, and in our case for radio, it's our audio signal. And we're just multiplying our audio signal times this carrier wave, the sine wave, to create the AM signal, the amplitude modulated signal. Okay. So this is all pretty basic stuff. I mean, this is all on the technician test. Everybody kind of would understand this. But let's take it a little bit further. Let's look at phase and frequency of the RF signal. Okay, so we can add another term into that sine equation, which is the phase shift of that sinusoid, sine wave. And also, so if we vary parameters such as the frequency inside that sine wave equation, or vary the phase versus, and in some cases, creating a frequency modulated signal or a phase modulated signal is a lot more complicated from a circuitry standpoint in often cases than doing just a simple amplitude modulation. So let's look at a couple of things that we can do here. So if we take that phase parameter and switch it between 0 and 180 degrees, we create a digital modulation type called binary phase shift keying, or BPSK. And this is often used in some of the digital modes and things like that. Now, I've shown it very abruptly in the graphic down below, where we're just inverting the signal, which creates a 180 degree phase shift. The reality is it switches between those two phases much more slowly, but this just kind of shows you the effect of doing a binary phase shift keying. But here's the interesting thing. What's another way to create a BPSK signal, okay, other than just changing the phase between 0 and 180 in some kind of a phase modulator? The answer is another way is to switch the A parameter, the amplitude term, from +1 to -1. Okay, so the key here, though, is that we've actually changed the phase by changing an amplitude value. And in some sense, that's a lot easier to do from a circuitry standpoint. It's a lot easier to change the gain invert the gain, not invert the gain, change the gain. It's a lot easier to do that oftentimes than to create a phase shift on an RF signal. So here we've figured out a way that, hey, I could just change this amplitude parameter and invert the phase of a signal, create a binary phase shift keyed signal. So that's kind of an important concept here. So keep that in the back of your mind. Let's talk about what's meant by the term quadrature. It's a big word, but it really is pretty simple. It really comes down to what is the difference between a sine wave and a cosine wave. And the answer to that is they're basically the same waveform. They're just 90 degrees apart. There's a 90-degree phase shift between them. If you shift a cosine wave the right direction by 90 degrees, it looks like a sine wave. And vice versa, you shift a sine wave by 90 degrees the right amount, it's a cosine wave. They're exactly the same waveform, just one is delayed with respect to the other one by 90 degrees, delayed or advanced by 90 degrees. So whenever you have two signals that are the same frequency, but out of phase by 90 degrees, they're said to be in quadrature. That's the name that's applied to that, called in quadrature, okay? So thus, by a sine wave, by their very nature, are waveforms that are in quadrature. And if we adopt the convention to say that the cosine wave, we'll call that the in-phase signal, okay, or essentially our reference, and abbreviated by the letter I for in-phase. The sine wave is then called the quadrature signal, or the Q signal. That's where we get the I and Q from in the when we talk about IQ signals. It really is just representing the phase relationship between two signals. Okay, so that's where the I and Q come from. So we'll let the I and the Q represent the magnitude, or that A parameter on a sine and cosine waveform. Okay, so that A versus time, that multiplier at the beginning of our sine wave, we'll just call it I when it's the cosine wave. We'll call it Q when it's the sine wave. Now, there's some very interesting things that we can do with quadrature signals. So all this, why do we care? Well, hopefully this next slide will help you to see why we care. Okay. So let's talk about the relationship of all this. And you may have, if you know, some kind of to some of the general or advanced test, you might have seen this diagram called a Phasor diagram or a polar plot, where the length of an arrow that we'll call a vector, the length of that arrow represents the magnitude or the amplitude of an RF signal. Okay. The angle of that vector off of the x-axis is the phase of that signal. Okay. But then if we take and project out the x and y coordinates, if you will, of that vector, that essentially is the I and Q components of that signal. Okay, so we're going to, we'll be looking at this Phasor diagram a little bit, but that's kind of where the I and Q come from. It's a way of representing the amplitude and phase. The amplitude and phase of any RF signal can be described by its I and Q components, because it's just the projection from that magnitude vector to the x and y axis. So there's some interesting things that happen when we add quadrature signals together. Okay, so for example, if I've got this diagram here that's showing I'm adding I times cosine plus Q times sine, right? If I is just a quantity 1 and Q is the quantity 0, it's like the sine wave's not there, the output is obviously going to be a cosine wave. Pretty simple, right? And firstly, if I is equal to 0 and Q is equal to 1, then the output, the sum of them, is going to be a sine wave. Okay, so again, by changing an amplitude value, we've created a phase shift on the output between sine and cosine wave. Okay. Now, if I and Q are of equal values, then the sum of them is going to be a sinusoid that's only shifted by 45 degrees. Okay. So we can see just by varying the amplitude of I and Q, we can vary the phase of that output signal. So essentially a phase modulator. Okay, pretty simple. By just varying the amplitudes of two signals, we can create phase changes and phase modulation. So if you vary I and Q anywhere between, in this case, generically between plus and minus 1, you can vary the output phase coming out of that summing junction to be anything between 0 and 360 degree phase shift. So you can kind of rotate and slide that sinusoid anywhere, to create any phase shift you want just by changing those amplitudes between plus and minus 1. So we can see how we can do a phase modulation pretty simply, right? So obviously adjusting I and Q up or down will also adjust the output amplitude, right? So if we, instead of making them plus and minus 1, we made them plus and minus 0.5. We'll get the same phase shift, but also we'll change the amplitude. So we can do amplitude modulation and phase changes and phase modulation just by changing the magnitude of I and Q. Okay. So that leads to something called quadrature modulation. And this is something that's used quite often in everything from Bluetooth and Wi-Fi to even some digital modes and things like that. So for example, if I and Q are varied over time, as we kind of described earlier, the amplitude and phase of the RF signal is also varied. If we basically use digital representations, just plus ones and minus ones to represent I and Q, what that will do is we'll create an output that will vary between one of 4 separate phases, right? And they're represented essentially kind of by the X's here, on this. Those X's actually should be rotated around probably here, 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 and here. You can see my arrow kind of going through. So we can create what's called a quadrature phase shift keyed signal by just multiplying our RF signal by plus and minus 1 to represent these symbols or bits that are being sent. Okay, and oftentimes this polar diagram will often be called a constellation diagram when the symbol locations are just indicated. So the more important aspect here is that the I and Q signals can literally be anything versus time. They don't have to be just plus 1 or minus 1. They can literally be really any analog voltage of some sort. And by doing that, any amplitude, phase, or even frequency variation of an RF signal can be represented by an appropriate, waveform on I and Q. As long as you apply the right combination of I and Q over time, we can create any kind of RF signal. Amplitude modulation, phase modulation, frequency modulation, single sideband, any type of RF signal modulation can be created by an appropriate generation of the I and Q to begin with. So complex RF signals, or complex modulation of RF signals, is just by creating the right set of I and Q, right? And those I and Q signals are often referred to as the quadrature signals, or often will be called baseband signals. These terms are typically referred to kind of interchangeably. Now this is all kind of describing kind of the transmit path, if you will. But all of that kind of works in reverse the same way. So any RF signal coming in that is can be quadrature demodulated with a quadrature LO, with using a 0 and 90 degree local oscillator to create the quadrature analog signals. So that's the same process works in reverse. And this is what happens inside of a software-defined receiver, where the RF signal coming in, sometimes it's down converted to some IF. Ultimately, then what's done is a digital down converter or quadrature down convert to I and Q data. Okay, and you get this I and Q waveforms essentially versus time. Oftentimes they're going to be sampled, and then those samples of the I and Q is what is mathematically processed inside the SDR to do the filtering, signal processing, and ultimately converting it back down to whatever that baseband signal is, whether it's a single sideband audio tone or it's a digital modulation of some sort. But it all begins with creating that IQ data. Okay, and this is what all software-defined receivers do inside them. These signals would then ultimately be sampled and create those samples, which will go into the microprocessor or digital signal processor to do the further analysis and filtering on them. Okay, and the point here is that once you have the I and Q versus time over a given bandwidth, you know everything you need to know about that signal. You essentially know it's the signal's amplitude and phase at any instant in time, and how that amplitude varies and how the phase varies over time. That also kind of defines how the frequency varies over time. So anything can be represented by the I and Q representation of the signal. Okay. So let's look a bit about the IQ processing. Really what we're doing is in a receiver, for example, we're taking a signal that's up at some carrier frequency, and the process of doing the down conversion to IQ is shifting that whole RF signal that you have up centered at the carrier frequency and shifting it right down to be centered on DC. So in reality, the IQ data only occupies half of the bandwidth that the actual RF signal does, because it's what's called a complex set of data. So you really get a positive and negative spectrum, but the actual sample data itself really only occupies half the bandwidth. So it gives you very low sample rates, pretty low. You don't have to sample the signal at something that exceeds the carrier frequency. We only have to sample the signal at something that exceeds essentially half the bandwidth of the signal. So, one of the things that you typically see on a software-defined receiver, for example, is some pretty complex displays, like the spectrum of what's going on over a wide frequency range. Okay, because with that frequency range that you see on the spectrum plot is really that frequency range that you see of that baseband centered signal around DC. And then the waterfall plot is just essentially a strip chart recorder, if you will, of the spectral activity over time. So, but once you've got this relatively low rate baseband signal, doing these FFTs over time to show you this kind of nice band scope type view isn't that computationally intensive. So that's why you see a lot of this on these SDR radios. So what about analog modulation? So how do we handle that? So for AM, if you simply vary the I and Q components together in unison, you're going to create an amplitude modulated signal. You're not going to change the phase. You're just going to change the amplitude of that signal. So that's how AM is created. PM, or phase modulation, is varying the I and Q at the correct level so that the angle is just rotated to whatever phase you want that output signal to have. Okay. FM is you're typically varying the I and Q sinusoidally, because a frequency modulation would be represented in this Phasor diagram by this vector rotating around either clockwise or counterclockwise around the circle. The speed at which it rotates around tells you essentially what the frequency deviation is. If you're not rotating around, you're static. You essentially got a continuous carrier that's not being modulated. If you rotated that vector around by varying I and Q appropriately to rotate that vector around, say once a second, that would represent a 1 hertz frequency shift. If you rotate once a second in the other direction, that's a 1 hertz frequency shift in the other direction. So FM is really represented by sinusoidal variations of I and Q that have the effect of rotating that vector around the polar diagram. Okay. And quadrature techniques are typically used for single sideband, what's called the phasing method of single sideband, as opposed to creating an amplitude modulated signal that has a carrier and 2 sidebands and then filtering one away. The phasing method takes care of it kind of just by the nature of the signals. So in this case, this is kind of representing a phasing method transmit chain where I've got the audio signal coming in, going into a pair of quadrature mixers. The signal also goes through a 90-degree phase shift network, so I've got a 90-degree phase shift on the audio as well as 90 degrees on the LO or the RF signal. And then if we take the output of those 2 mixers and we add them, we might get upper sideband. If we subtract them, we get lower sideband. So if you have a variable gain stage that can invert one of the signals or not, you can actually get upper sideband or lower sideband without even having to apply a filter. And this is what's typically done in a phasing method, single sideband, both generation as well as receive. So just a sign change at that summing node, which is again 180 degrees phase shift, or simply inverting one of the signals, you can select the upper and lower sideband without using any filters at all. So this is something that's commonly done as well. So this was really just a touch on what IQ signals are, how they're processed. So if someone talks to you about what IQ is, it gives you an idea of what you're talking about, and at least you're not completely in the dark about it. So I didn't want to spend a whole lot of time, kind of going over all the math of it, because the math is no fun. But at least to get an idea of what those signals are, and so it's not completely foreign to you. That was really the intent here tonight. So I'll stop the share here. If there's any questions that pop up in the chat or something like that, we can go take a look at that.
All right. Well, I tried to pay attention, Alan, as much as I could, but I was also looking at this internet issue. This is some heavy stuff. I mean, you're definitely an expert in talking about this. I think my IQ needs to be a little bit higher, though, to understand much of this.
Yeah, it's one of those things that I looked through my YouTube channel to look for the most popular or ham radio related videos that I had. And this IQ, I've got a couple of videos on the basics of IQ, and they've been viewed close to 300,000 times. So I thought there was probably enough curiosity out there that it was worth kind of going over on the roundtable here today.
Yeah. Well,
it helped me because I was always confusing the quadrature with quadraphonic.
Okay.
From back in the 70s.
Yeah. Oh, absolutely.
Yeah. So I've been watching the chat room. Some people are getting it, some people are not getting it.
Okay.
And I was trying to do a quick search on internet outages. It's very possible we could have some major internet issues going on in this part of the country. I'm trying to figure that out.
Yeah, I think so, because for a while there, my local internet connection, which is usually very stable, started dropping out. So I think there's, big cable cut or something like that somewhere.
Well, and Alan, what we'll have to do, hopefully it recorded fine.
Okay.
And we get more of our viewers that watch this after the fact, after the show is live. So
sure.
Over the next few days, we'll probably get more people, and we do get some comments in the questions there. So we'll see how it goes. And
like I said, I do have a couple of videos. If you just go to my YouTube channel, youtube.com/W2AEW, and then you do the search that's down, below the main graphic, and just put in IQ there, you'll come up with all the videos that I have that deal with this. And the good thing about doing the videos, I can actually show some things on the oscilloscope and that type of thing to help illustrate some of this stuff. And so, it's easier to do in that video than I was able to do here live. But like I said, hopefully it's just enough to maybe clear up a little bit of misunderstanding you had. Didn't want to make you, not enough here to make everybody an expert, but just to, add one little nugget in the back of your mind.
For sure, and hey, we thank you for talking about that tonight. And I'm sure there, as any group, you've got people that comprehend that, and that's exactly what they want to hear. And then you've got other people that want to hear things at a much lower level. So it's very hard to get something out there for everybody.
Sure.
Okay. But we'll see how it goes, and we'll see what the comments are here. If it got out and it got recorded, I'm not sure that it really even recorded right.
Yeah, I wonder, since you had to restart the stream, if you had to, if that.
Well, I'm looking at the YouTube dashboard, and it's showing it's way behind right now as far as the stream, but I think that. And also, we're getting a message, poor stream quality, stream health. So I don't know, it's going to be probably a full day of testing tomorrow, and if I have to beat up the Comcast people or Xfinity, whoever it is, one's TV and one's internet, we'll be on them tomorrow.
Well, I'm AT&T, so it may be broader than just Comcast.
I saw something in a search a minute ago about ATT major outages through Nashville, Knoxville, and that area. So,
but Comcast is probably going to lease a lot of stuff through AT&T.
Yeah. So Russ is saying everything looking good there. So I don't know, man. It just we'll just have to see. It just really upsets me though to have issues like this, and we want to try to put on the best webcasting show as we can, and we have technical issues like this. They're a little discouraging, but we're not going to give up.
Yeah, we're putting together a pretty long list of topics for future videos. So obviously, any listeners out there that if you've got topics that you'd like to hear on future tech tips, certainly let us know, and we'll keep building the list and pick from those lists each week and try to come up with some topics that'll be of interest to everybody.
Yeah, send us through your list. We'll put something together for you there. All right. Let's move over to Glenn and see if we can get through this without going down again. So Glenn, how's it going, and what are we going to talk about tonight, Glenn?
Well, I was just going to show a couple pictures.
Okay.
See if we can't figure out how to share my screen and hope it works.
Yeah.
Let's see here. Which screen am I trying to share?
Yeah, this thing is looking good now.
Of
we'll
course,
see.
yeah.
But I'm still showing poor stream health.
This is the screen I want to share, and it's not showing up
Now-
as a screen
now
that I can share.
Yeah.
There we go. All right, we'll hit this one.
All right. Not seeing anything yet.
Yeah, give it a minute. My computer has to think on this because it's Windows 7. There we go. Are you getting the screen share now?
It just
Yeah.
tried to cue. Yeah, it's starting.
get
Yeah,
its
there we
act
go.
together.
There we go. Okay, Glenn.
There we go.
Yeah.
Well,
it has to change.
what are we looking at, Glenn? Talk to us.
What you are looking at there is, let me hang on a minute. Did I just lose my screen share?
You just covered it over.
Yeah.
Hmm.
Too many stuffs.
Yeah, it looks like it's sitting behind there.
That's what I thought, but I moved it and it's not there.
We're going to have to send you to Zoom school after I get back.
Probably.
Yeah.
Yeah, because it is.
So.
There we go. Well,
I think you got it. Okay. Just open a file up and it'll
trying to
probably
get
play.
there. There we go. Is it back up?
Yeah, it's up there. Uh-huh.
It
Okay.
is there.
I won't touch anything else then. That is the inside of an AR-40 built from scratch. The low-end CDE high-gain rotator controller. We took it and gave it Arduino control
Uh-huh.
so that you can interface it with ham radio deluxe and everything. And it actually operates the same as an AR-40 as well. So that's a standalone, and you can interface it to the computer. And then some of this is actually an Arduino. Some of us may be old enough to remember the old DEC PDP-8 series of mini computers. And that was actually the first computer I ever worked with. Well, they are now emulating a lot of these, and this is actually an Arduino-powered emulated DEC PDP-8. It will actually run all the DEC software and everything. And that comes as a kit, and I got that kit. And for those of us that are into the PDP-11, they have a similar kit. This one is Raspberry Pi powered. And that's going to be my winter fun projects. And here we have another of the book projects. We can plug into the serial port on like the Yaesu FT450, 950 and everything, and pull out the CAT data from it and give you a remote VFO display and CAT control capability, because this is a touch screen display. So you can actually create touch screen and display of your Yaesu CAT display, and you can do that for a lot of the current Yaesu rigs. And those are just a couple of the little things I've got going on in the new book and around the house. I figure each week I'll have some new pictures. I've got literally hundreds of pictures. Let's go ahead and stop sharing here if I can.
So, are you going to have a section on building that rotor control in your book?
Yes.
And is that an expensive project?
No, not really. I think the hardest part is the transformer.
Uh-huh.
You'll need to power it. It's just a 28 volt AC transformer. And,
Okay, that's not bad.
no, and that was really, everything else is cheap. It's just a, couple of bucks to actually build.
Is that right? It looks like it had
Yeah,
a lot
let me
more.
look at
These
lot
days,
more
probably
in it.
the housing is probably the most expensive piece.
Yeah.
Yeah, and that was just a chunk of aluminum. God knows where I got that. I think it's actually a 10-tech enclosure I got years ago. But there's only, a handful of relays, the transformer, the motor capacitor, and, a voltage regulator and a nano in the display. So
And what kind of
probably looking
what type rotor does that control?
that is the AR-40 that's currently being sold by MFJ. It's the low-end
Yeah.
antenna rotator that they have. It's about a $200 and something rotor and controller.
And does that rotor just have a pot in it for direction?
Correct.
Okay, I think.
It has the direction pot, and you just press the start button after you turn the pot, and it rotates that position. And I wanted to take that and give it the interface to Ham Radio Deluxe so I can remote control the whole thing.
So you basically just take your Arduino and you calibrate it with that pot for your north, east, southwest, and it remembers it, and it just.
Well, it's even easier than that.
Yeah.
I mean, with your rotor controller and the rotators, typically they just have a 5-volt or a potentiometer in there, and the 0-volt position is full north, and then a full 360 rotation later is the max voltage condition, and all you have to do is convert that down to a 0 to 5 volt level and convert it to DC, and it's calibrate your 0 and calibrate the max, and it's the old trigonometry, y equals mx plus b formula, and calculate your degree position from there.
That's cool. And a lot of the programs now, or some of the programs like Ham Radio Deluxe, it'll actually interface to that and control it.
Yeah, this box actually emulates the Yaesu GS232 control box. So as far as Ham Radio Deluxe is concerned, it's turning a Yaesu GS232 rotator, or control box that turns a Yaesu rotator. It doesn't care what it's really talking to as long as it gets the correct command information back.
All right, so I need to look into something like that. Now, I've got azimuth and elevation. You got
Correct.
anything built in to do the elevation?
Actually, in my second book, this one, we actually do that.
Okay.
With the Yaesu, did I do that in this book or the first book?
I don't think it
But
was.
yeah, I do the Yaesu
Yeah.
G5400, G5500, but the more I'm thinking about that was in the first book. I was in this one that you can't get anymore.
Yeah, the rotor, Glenn, the rotor I've got, the control box, I think it says Alliance on it. It's got the,
Correct.
I'm not sure what rotor is out there. It's a pretty good sized rotor, but it's not a high-end dollar, rotor.
Gee, the only Alliance one I know off the top of my head is the U100, and that's a really old one. But yeah, here we go. That's in the first book on how to do the ASL controller.
Okay.
And that's really the hard part, is just getting the Arduino to emulate some form of rotator controller that Ham Radio Deluxe will talk to, and give it the correct position and control information back so Ham Radio Deluxe can control it. And there's some very good code out there for the Yaesu GS232, and everybody supports that. So that's
Now,
what I chose to use.
do you have to have some type of monitor plugged in with that, or are you? I guess you're using your monitor on your computer with like HRO, or Ham Radio Deluxe.
Yeah, on
right?
Ham Radio Deluxe, you actually have your world display on there, and you just point to the country you want your antenna to go to and click, and off it goes.
Well, so cool.
So, but I also took a this is pretty much a scratch built control box. If you have an existing AR40 control box, you can take that and just modify it, and it's just like a couple of trace cuts on the board, add the Arduino and the relay board, and poof, hook it up to Ham Radio Deluxe. So I take it several ways.
Well, Glenn, you must be good luck, because I'm looking over here and an excellent green light on the health, stream health. It's not flickering while you're on. I don't know what's going on here.
I don't know. Like I say, it was affecting me as well, so I think it's some kind of wide area issue.
Yeah.
And typically for us, that's a cable cut. And I haven't been made aware of one, but most of the major ones in Mississippi I will hear about, but with the schools being closed at night, I probably won't see anything on their mailing list unless it continues on until the morning.
All right. Well, I tell you, the show tonight tired me out.
Yeah,
It
I
really
can
did.
bet.
It tired me out, and gee, I don't like what went on tonight, but it was beyond my control. We'll definitely be doing a lot of testing this weekend on our network to make sure.
I think it was just the internet itself.
Yeah, to make sure it's not here and that it's
No, I don't think it is.
somewhere
I
else.
think it's because your signal is actually doing a lot better now as well.
Yeah, I mean, it's the dashboard shows excellent health, and I mean, everything's perfect. So anyway,
Keep in mind, this was
we'll be working on that. And hey, this week, some of you guys, probably many of you didn't know it, we had an impromptu get-together, ham radio get-together, and several people missed it. They got in a little late and sent me emails that they would like to have attended. We may do that again, maybe once a week or something. I'll post maybe a link in our Facebook group that we're going to have an impromptu ham radio get-together, on a certain night at 7 o'clock, and you guys have to bring your own snacks and bring your own drinks, and we'll just have a good time. We had about 10 or 15 people on yesterday, and we just talked about a lot of different things. No structure, no specific topics. So that will give an opportunity to a lot of you guys out there to to join us, to join the group here and become closer in the group and ask questions. So we'll try more of that. Don't forget our 40 meter net on Tuesdays, and also if you're listening on WBCQ on 6160, please send us an email to tom@w5kub.com, tom@w5kub.com. We'd love to hear from you. Our shortwave broadcast is delayed. It's not exactly live and matching up with our live show each night. But you're hearing the exact same show. It's just delayed. And we did that because of the time slot we had to move into. So we'd love to hear from you. Man, I don't know of anything else to do tonight. I'm wore out. The internet outage wore me out, and I haven't had dinner yet, so I'm going to go get some dinner. And I'm going to say good night to everybody. Glenn and Alan, you guys got anything else you want to talk about tonight?
No, I think I'm good on my end. Like I said, I know it was a little bit of an esoteric topic tonight, but I guess for those that are playing around with SDRs and things like that, hopefully it just turned a light bulb on or two. But we'll work on another topic for next week. And maybe we won't go as deep technically, but look at some more practical things. But we'll figure it out between now and then. For any listeners that are out there, be sure you can shoot Tom or myself an email with some ideas of what you might like to see on a future Tech Tips segment, and we'll get it scheduled in there. So, but that's all from me.
All right. Good night, everybody out there. Thanks for joining us tonight. Sorry about the issues. We think it was a wide area internet issue, maybe possibly a YouTube issue, but we're going to have it figured out before next weekend. 73 to everybody out there.